You've probably heard that old saying about the wisdom of the crowd, right? The idea that a whole bunch of people are usually smarter than just one expert. Well, what if you could teach a computer that same trick? That's exactly what we're going to break down today as we get into one of the coolest and most powerful concepts in machine learning, the random forest.
So here's how we're going to do it. We'll kick things off with that crowd analogy. Then we'll meet the single building block of the whole thing, the decision tree. After that, we'll see how a smarter forest gets built, how it actually makes a final decision, and then we'll weigh the pros and cons. And to wrap it all up, we'll look at where this stuff is actually being used out in the wild.
All right, let's dive right in. To really get what a random forest is all about, we don't need to look at a single line of code. All we need is a simple story you can probably relate to.
Imagine you need to buy a new car. You could go with option A, ask your one friend who's a total car fanatic. I mean, they know a ton, but what if they secretly hate a certain brand you like? Or they only care about horsepower? Their advice is powerful, sure, but it's also kind of risky. Now, what about option B? Instead, you ask 100 different people. Your cousin who's a mechanic, your coworker who commutes 2 hours a day, your neighbor who just wants good gas mileage, and you tally their votes. You'd get a much more reliable, much more balanced answer, right?
And that, in a nutshell, is a random forest. It's the machine learning version of asking that big, diverse crowd of friends for their opinion. It's all about strength in numbers.
Now, the fancy technical term for this is an ensemble method. And ensemble is the perfect word, really. It just means a group working together in harmony. Instead of putting all our trust in one single model, we're building a whole forest of them and then combining all of their answers.
So if the whole forest is our crowd of friends, who are the individual friends? Well, it's time to meet the fundamental building block of it all, the decision tree.
A single decision tree is actually pretty simple to understand. Just think of it like a game of 20 questions or a flowchart. It's just a series of yes or no questions that it asks about the data to slice and dice it until it lands on a final conclusion. Each one of these trees is an individual model in our forest.
Let's take a simple example. Say we're trying to figure out if an email is spam. The tree might ask, does it have the word winner in it? Yes. Okay, next question. Is the sender someone in your contacts? No. The tree follows this simple path and boom, it makes its conclusion. It's probably spam. See? Super clear. But there's a big problem with just relying on one of these.
And here's the catch. A single tree all by itself can get a little too good. It doesn't just learn the general rules from the data, it starts to memorize the specific examples it was trained on, including all the weird quirks and random noise.
This major problem has a name. It's called overfitting. And what that means is the model is brilliant when you test it on the data it's already seen, but it completely falls apart when you show it something new. Think of it like a student who just memorizes the answers for a practice test, but can't actually solve a new problem on the final exam. This is exactly why we need a whole forest, not just one tree.
And that brings us to the solution, which is where the real magic happens. So how do we stop all of our friends from developing the same exact biases? Well, we build a smarter forest by injecting a healthy dose of randomness.
The first trick is something called bagging, or sometimes you'll hear it called bootstrapping. Instead of showing every single tree the exact same complete data set, we give each tree its own unique random sample of the data. So tree number 1 gets its own little bag of data to learn from, tree number 2 gets another, and so on. This is huge because it guarantees that each tree is going to have a slightly different perspective on the world. It stops any one tree from thinking it's seen it all.
The second trick is even cooler. When a tree is trying to decide what question to ask, we don't let it look at all the information it has. We actually force it to choose from a random, limited set of features. It's like telling one of your car shopping friends, hey, you can only think about the car's safety and price, and telling another one, you can only look at its engine size and color. This forces them to find different, more creative paths to an answer, which makes the entire group way more powerful. Okay, so we've built our big, diverse forest. We've got hundreds of unique trees, and they've all learned from slightly different data, and we're forced to focus on different features. So now what? How do we get one single, final answer from all of them? Well, it's time for the crowd to cast its votes.
It really comes down to two simple methods. If we're trying to put something into a category, like spam or not spam, which is a task called classification, the forest just takes a majority vote. If 80 trees vote spam and 20 vote not spam, well, our answer is spam. But if we're trying to predict an actual number, like the price of a house, that's called regression, the forest just takes the average of all the individual predictions. Super simple, democratic, and really, really effective.
Now, as much as we love it, a random forest isn't a silver bullet. It's not perfect. So it's really important to get a handle on both its biggest strengths and its potential weaknesses. Let's take a look at the scorecard.
So on the pro side, it's known for being highly accurate. That whole wisdom of the crowd effect really pays off. It's also fantastic at dealing with messy, real-world data that might have missing pieces. And most importantly, because of all that randomness we talked about, it pretty much eliminates that overfitting problem. But there are downsides. The big one is that it can be a black box. I mean, how do you explain a final decision that was based on the votes of 500 different little models? It's tough. And of course, training hundreds of trees is going to be slower and require more computer horsepower than just training one.
So with that trade-off between amazing accuracy and being hard to explain, where does this algorithm actually get used? Let's check out a few real-world examples where that accuracy is what matters most.
You can find these things everywhere. Banks use them constantly to predict if a customer is likely to default on a loan, a classic yes or no problem. In healthcare, they can help doctors predict whether a patient has a certain disease based on a whole mess of symptoms. And yeah, in finance, they're used to try and predict whether a stock price is going to go up or down. Basically, any situation with complex data where you absolutely need the right answer, random forests are a top choice.
And that leaves us with a really interesting question to chew on. We know the forest is often more accurate, but we also know it's hard to interpret. So if a black box algorithm tells a bank to deny someone a loan or tells a doctor to make a particular diagnosis, but we can't fully explain why it made that choice, should we always trust its answer? That's the big trade-off between raw performance and being able to explain things, and it's something we're all grappling with more and more these days.